Today we're going to start our new unit, Properties of Transformations. So our first section here is going to be translating figures and use vectors. So I will define a vector here when we get to that point. So if you go ahead and get to section 9.1, I do have a couple of definitions already here for you. The first word I want to define is the word image. So the image is defined as a new figure that is produced from the transformation of another. So I like to think of the phrase image or the word image as like the answer after some sort of transformation has occurred. So a new figure that is produced from the transformation of another figure. Pre-image is just the original figure. So you have an original figure and then a new figure. So the original is pre-image, the new is image. Also, when you were working with like symbols and notation, let's say you have point A. So you would, of course, just have point A. To show that the image is different from the pre-image, oftentimes it's shown like this. So that little tick mark there is considered, it's called prime. So when you see that prime, you're going to know that's the answer, and then the one without it is just the original. The last word here is isometry, and isometry is a transformation that preserves length and angle measures. So with isometries, they're basically congruent shapes. So I'm going to write congruent here. And if you look at the next theorem, that is showing us an isometry with a translation. So a translation theorem says a translation is an isometry. So what that means is the original shape and the image, the pre-image and image, are the same size. Nothing has grown or nothing has gotten smaller. It's the same size. Okay, let's actually do a translation here. We're going to graph it and go ahead and write it over to the side. So we are going to graph the quadrilateral with the vertices and the directions. We're going to find the image, and using this, this is called coordinate notation. Then we're going to use prime notation, and we will also define magnitude. So will you go ahead and plot A, B, C, and D? So 1, 2, 3, 1, 2, 3, 4, A, -3, 7, and then 2, 8, and then 2, 4. All right, so let's connect. Looks like a trapezoid here. Okay, we want to find the image of each vertex after the translation, and then we're going to graph it. So we are going to take this translation, and so I'm going to start by, I'm going to rewrite my vertices vertically. So I'm just going to recopy the 4 ordered pairs. Just on this first example, I want to show you one way to, there's 2 ways to do this. One way to do it is just by plugging in the numbers. And then D is at 2, 4. Okay, so if I want to translate, I want to take point A and I want to translate it into A prime. So what I can do here, one way to do it is to take the x value of -3 and plug it in for x in the directions. So if I do that, if I take -3 and I plug it in for x and do the math, -3 plus 4 is 1. Do the same thing for the 4. I want to plug it in for y here, and so if I do 4 minus 3, I get 1. So I just happen to get 1, 1 here. Oops. I was trying to fix that parenthesis. Okay, so I could do that for each of the 4 vertices. Okay, so let's go ahead and do that. So B prime, I'm going to plug -3 in again. So I'm going to get the same thing. So -3 plus 4 is 1. Plug 7 in for y. So 7 minus 3 is 4. C prime, plug in 2. 2 plus 4 is 6. Plug in 8. 8 minus 3 is 5. And then D prime, we've got 2. 2 plus 4 is 6. And 4. 4 minus 3 is 1. So let's graph those. And I'm going to graph them and call it A prime, B prime, C prime, and D prime. So 1, 1. I've got 1, 4. I've got 6, 5. And then I've got 6, 1. So I want you to see how it is a translation, so it's translating to the right and down. So if you look at the, if you think about the x-axis, to the right is going up, to the left is going down, so adding versus subtracting. So if you look at your coordinate notation, I'm taking x and I'm moving 4 units to the right. So if we take C to C prime, see how I went 1, 2, 3, 4 units to the right. The y value says go subtract 3. So subtracting 3 would be moving down, so it's down by 3. So what I could have done is I could have taken the graph and I could have just done counting. I could have said over 4 down 3 and I could have plotted. And I could have done that for every single point. All right, so that is an alternative way to do that. So I now have, there's my prime notation. So the magnitude of something, maybe I'll write that over here to the side. The magnitude of something is really the same as the distance. So I'm going to add over here magnitude. So for magnitude, I'm going to find the distance from one pre-image to the other. Find the distance from one pre-image to another. All right, so let's maybe work with, let me do some highlighting here. Let's work with possibly, let's work with A to A prime. Okay, actually, I miswrote over here. We don't want to go from one pre-image to another. We want to go from one pre-image to image. So I want to stay from the original point to the other. So what I want to do is I want to find the distance between A and A prime. So I could do distance formula, okay? So if I did distance formula, I would have to work with that formula, x2 minus x1 squared plus y2 minus y1 squared. I also could do Pythagorean theorem. So I'm going to show you Pythagorean theorem again. So if I did Pythagorean theorem, I'm going to take my green segment as the hypotenuse of this right triangle that I sketch around it. So if I have a right triangle, then I can count out, so vertically it's 3 units, horizontally it's 4. So I could do 3 squared plus 4 squared equals c squared, and that's my green segment. So 9 plus 16 equals c squared. So I've got 25 equals c squared, and then when you come through here and square root, you get 5. I would have still gotten 5 over here if I would have done distance formula. So the magnitude is 5. So I'm going to add here 5 equals magnitude. Okay, so if you want to do distance formula, that's fine. But if you're already working on a graph, you might just switch over to Pythagorean theorem. Okay, let's move on. This time, let's write the rule. So write a rule for the translation from triangle ABC to triangle A prime, B prime. That should say C prime. All right, so when I write my rule, it's going to be in this format back here. It's going to be in this highlighted format. So I'm going to start out with this, x comma y, and then an arrow. So let's begin with, so for every x, oops, gosh, sorry, for every x comma y, so when I draw my arrow, it's basically saying every single order pair is going to go through these directions. So I'm going to take the x value and try to figure out where it's going. So if you look at, let's maybe go from, let's not work with A because it's not on a coordinate. Let's work with, let's see. Well, we can work with A. This one, now that I look at it, is a little bit tricky. So this is going by 2 units. So I guess we could say that A is up here at 2, 4, 6, 7. Okay, so that's at 7 units. And A prime right here is going from, it's going over, let's write that out. So let's write out A is at 0, 7. Might be a little easier. A prime, let's look at that. So it's going over 2.5. So that's really over 3 units since my graph is by 2. And then it's going up 2, up 4, up 1 more is 5. All right, so let's look at those values. So I'm going from 0 to 3. So I am going up by 3. So that is going to be written as x plus 3. Now I'm going from 7 down to 5 on the y values. So I'm going to go decreasing. So I want you to think decreasing is subtraction. So every y value is going to be going down by 2. And so that right there is my rule. Okay, so we often call this coordinate notation. Coordinate notation. Okay, so it's a good way to list out what is happening with every x and y. Okay, let's keep going. All right, so here's a little bit more information about this idea of a vector. So a vector is a quantity that has both direction and magnitude. So direction tells you, of course, that's pretty self-explanatory. Magnitude is more of a length. And it's represented by a coordinate plane by an arrow drawn from one point to another. So see down here, you've got point F to G. So it goes from, oops, excuse me. We are going from F to G. So there's only one arrowhead on it. So that's considered a vector, not necessarily a ray. So the initial point right here is the starting point of the vector, so it's point F. Notice there's no arrowhead. The terminal point, which is the same as ending point, is G. So it's the one with the arrowhead. So I'm going to put here arrow and then no arrow. Now, the magnitude is the distance between the image and pre-image. So it's kind of like a length. There's also going to be this horizontal component. So you can see that's sort of like what we just did with our Pythagorean theorem. So in this case, this vector is going to the right 5 and it's up 3. So that's your vertical component, of course, is the value moving up. All right, component form of a vector. I want us to write a couple of things. First of all, the symbols of a vector are these. They kind of look like a greater than or less than sign. So I'm going to do this symbol and I'm going to write the word horizontal, comma, vertical, like that. And so we're going to use positive or negative for direction. So use plus or minus, should be a minus sign there, for direction. Okay. All right, so let's go to the next page and we are going to name all this out. So identify vector component. So let's name the vector and write its component form. So when I go to name this vector, I'm going to still work with the 2 letters of the points. And so it's going to look like this above AB. It looks kind of like half of an arrowhead, but notice that the this mark here is above the final point, and this is the initial point. Now, the component form is going to tell us the direction. So from A to B, it is going horizontally 1, 2, 3, 4, 5, 6, 7. So 7 to the right is positive, and then it's dropping vertically 1, 2, 3, 4, 5. So 7 comma negative 5. Okay, so horizontal comma vertical, and that's kind of the names are actually I should say the letters are telling me what direction. Okay. Let's go through one more. Actually, I'm going to do this last example in the next video. So will you go ahead and move on to that next video and watch me go through that last example?